In this video, we're going to be discussing the forces that hold molecules together, and we're going to use this in preparation for learning how these forces affect molecules in the liquid and solid state, and what kind of properties those will exhibit. You are going to need your notebook, you're going to need something to write with. You shouldn't need your periodic table for this because the molar masses I've already calculated for you. But once you have all those ready, let's go. Okay, so the first thing that we should probably look at when we do this is look at some of the properties of matter in different states. And what I'm going to do is I'm actually going to be comparing the gas state into the solid state, right? So if we talk about particles in a gas, they are in constant motion, they're spread out as much as they possibly can, right? They take up the entire volume of the container, no matter how large the container is. Because they're so far apart, they don't get any interaction with any other gas particles. And also, because they're so far apart, it's really easy to compress them into a smaller volume. But if we look at a solid, the particles in a solid aren't really moving that much. Like, the only movement a solid will kind of have is its molecules will kind of vibrate in place a little bit. Particles in a solid are extremely dense, which means they're packed very tightly together, and because they're packed tightly together, they're not very compressible. You can't pack them even smaller. So what do we learn from this? What we have to learn is that there is something that's keeping those particles in a solid held together to keep them as close as they are, but those things that are present in the solid are not present in the gas, right? So there has to be some attraction there in the solid state. And this is where we get to the idea of what's called an intermolecular force. An intermolecular force, I'm going to abbreviate it as IMF, is any attraction that holds one molecule to another molecule. Now, to keep in mind, these forces, while they may be strong, they are nowhere near as strong as chemical bonds are, right? So your covalent and ionic bonds are much, much stronger than the forces between molecules. And the bonds are what we call an intramolecular force. Intra meaning inside the molecule, right? So bonds are the attractions that hold atoms in a molecule together. Intermolecular forces are the attractions that hold one molecule to another molecule to another molecule in a large sample of that substance. Now, the stronger the intermolecular forces are in a molecule, the more difficult the particles of that molecule are to separate, right? Just like we were talking about when we were doing periodic trends, the stronger the attraction the nucleus had for the valence electrons, the harder those electrons were to remove, the harder it was to separate them. Same thing here. The stronger the attraction between the two molecules, the harder it's going to be to separate them. And the way that we're actually going to measure this is we're going to use melting point and boiling point as indicators of the strength of intermolecular forces, right? Because if something has a stronger intermolecular force, it's going to have a higher melting and a higher boiling point because you require more energy to separate them. Okay, so that's kind of how the forces work in general. We're going to get into three specific forces. The first force we're going to cover is what's called dispersion. You'll also see this referred to as London dispersion. The idea behind dispersion force is that the electrons in a molecule can move about in random motion. And when they do, occasionally you'll have it so that one side of the molecule has more electrons than the other side of the molecule. If that's the case, then the side that has more electrons is going to be slightly negative. The side that has less electrons is going to be slightly positive. This creates what's called a temporary dipole. Right? Dipole meaning separation in charge, plus side, minus side, just like our polar bonds. But temporary because as soon as the electrons go back to their original distribution, then that separation is gone. Now, the strength of this attraction, so the strength of this, is proportional to how many electrons are in the molecule and what the surface area of the molecule is. The way we're going to approximate number of electrons, by the way, instead of adding, is we're going to use molar mass. Because typically the heavier a molecule is, the more electrons it's going to have. And the reason why this force works the way that it does is, imagine I have a molecule, temporarily the side closest to me is plus and the side furthest away from me is negative. Well, what that can do is that can actually affect the molecule next to it. The negative side of the molecule closest to me can turn the other molecule's closest side positive so that they can attract. Right? Think of it kind of like a domino. We have our stack of dominoes, and the dispersion force is us just toppling it over to create that temporary separation in charge. So one will affect the one next to it, affects the one next to it, all the way down the line throughout the entire sample. And that will cause the sample to be held together. Right? But these are temporary, so as soon as the electrons move back, this goes away. But samples usually have a large enough number of molecules where some molecules will exhibit dispersion at any given time. Now, when it comes to figuring out what has dispersion, this is easy. Everything has dispersion unless it's a gas. So every liquid, every solid, every solution has dispersion force. That's the easy one, right? So everything has it. Now, if we kind of look at the two comparisons I gave you, how strong they are, the first one we'll look at is number of electrons, or molar mass is, again, our analog for this. So the thing to keep in mind here is that these are all liquid elements here. So we're looking at boiling point, which means we're looking at the liquids and what temperature at which they will turn into a gas. So while it says noble gases, these are actually noble liquids. Now what we can do is, if we look at the molar mass gets bigger as you go down, right? Helium's the lightest, then neon, then argon, radon is the heaviest. The boiling point increases as the substance gets heavier, right? So helium has a very low boiling point. Radon has a much higher boiling point. It's still a gas at room temperature, but if you can cool it down past -60, it will wind up being a liquid. Right? So the heavier the substance is, the stronger its dispersion force is, the higher its boiling point is, or the higher its melting point will be. Okay, so that's how dispersion works with molar mass. Now we'll also talk a little bit about surface area. So here what we have three different versions of the molecule pentane. Pentane is C5H12. On the right, we have what's called N-pentane, which is your normal 5-carbon chain. Cylinders tend to have very large amounts of surface area, right? So one of the ways to think about surface area is kind of like friction. So if you pass one over the other, the more surface area you have, the more friction you create when you drag across something. That's an attraction. So N-pentane has a lot of surface area, which means it has a very high boiling point compared to the other versions of it. Isopentane, what you do is you actually take one of the carbons on the end and you move it into the middle. It has a little bit more of a spherical shape, but still not completely spherical. And notice, spheres have less surface area than cylinders do. So as we lower the surface area, we lower the boiling point because there's less attraction. Neopentane, the one on the left, is spherical. Spheres have the smallest surface area for their volume. Since it has the smallest surface area, it has the smallest region over which to affect, which means that it's going to have the lowest boiling point. Right? And that's why that one says 9.5 C. So the higher the molar mass, the higher the dispersion, the higher the surface area, the higher the dispersion, the larger the boiling point is going to be, the stronger the attraction. Okay, so that's how dispersion works. That's our first intermolecular force of the three that we're going to be covering. Our second is the force so nice they named it twice. This is called dipole-dipole force. Dipole-dipole force will exist between any two polar molecules. The reason why is because how we said with dispersion, one side will be positive, one side will be negative temporarily. In a polar molecule, one side is always positive, the other side is always negative. So because those charges always exist, that attraction is always going to be there. You don't have to worry about it going away. Now, because the charges involved are larger and more permanent, dipole-dipole force is generally stronger than dispersion force is going to be. Right? So on a molecule-to-molecule basis, dipole-dipole is stronger than dispersion. And the strength of dipole-dipole is based on how polar the molecule is. So in this case, HCl, you would figure out the difference in electronegativities, and that will tell you how polar the bond is, and whichever one is more polar is going to have the stronger force. Okay, so this is our second force, dipole-dipole. Our third force is one that you're already familiar with. This is hydrogen bonding. You learned a little bit about this last year. Hydrogen bonding is basically taking dipole-dipole force and putting it on steroids. Right? It is a much, much, much stronger version of dipole-dipole. The reason why is because the three atoms that have to be involved in a hydrogen bond are nitrogen, oxygen, or fluorine. Those are the three most electronegative elements on the table, so they form the three most polar bonds when you connect them to hydrogen. Right? So any molecule that has a hydrogen physically bonded to N, O, or F will exhibit hydrogen bonding. It's not enough for the molecule to have hydrogen and nitrogen, oxygen, or fluorine in it. They have to be physically bonded to each other. Right? And my bad 80s pun here, the way you think about hydrogen bonding is that hydrogens, they just want to have fun. So as an example of how strong hydrogen bonding is, this chart that I have coming up on this slide shows you the boiling point of a bunch of different compounds. Now notice those three compounds, NH3, HF, and H2O on the left-hand side. You see how their boiling points are significantly larger than anything else in the same color scheme, right? The color scheme, by the way, goes down columns. So the light blue one, is all of the hydrogen compounds of group 16 elements, oxygen, sulfur, selenium, tellurium. The red one is group 17, the green one is group 15. Right, but again, notice, NH3, HF, H2O, much, much higher boiling points than anything else in their column, and also significantly higher than that of CH4. The reason why is because NH3, HF, and H2O will form hydrogen bonds.